Okay, so well, we have some preview exercise to start with, so I'm going to have you get started with those. Just take 10-15 minutes, and then we'll come back together and discuss. Okay, here we have two sets of ordered pairs. In which set does each x coordinate get paired with only one y coordinate? Yes. Set 2, we have 5. Sorry, set 1. Yeah. Because in set 2, you have a 5 getting paired with a 1, and then a 5 getting paired with a 2. So that's an x coordinate of 5 getting paired with two different y coordinates, right? So it's definitely set 1. All right, if I want to graph 2x and 2x plus 4 on the axes, basically when you're going to plot a graph or a line in particular, you just need a few points. You plug in a few x values, you get the y value. So a lot of people asked me about this sentence. It was just telling you what x values to plug in. That's all. Pick some x values between -2 and 2 to get your points. So if I plug -2 into y equals 2x, in fact, let's just do this. Let's keep our work organized. Then y would be 4. And if I plug in 0, y would be 0. And if I plug in 2, y would be 4. So I did 3 points. All right, so I've got -2, 4. Oops, this is -4. 0, 0. Why did I switch to -2x? Thanks. That's just plain old 2x. So that's -4 and that's 4. Okay. -2, -4, 0, 0, and 2, 4. Okay, so that makes a line. And then y equals 2x plus 4, I can make a separate xy chart. Let's do the same x values. -2, when I plug in, I'm going to get 0. And when I plug in 0, I get 4. And when I plug in 2, I get 8. So I have 0, -2, 0, 0, 4, and 2, 8. Okay, so that makes another line. All right. And use this graph to solve the problems. What is the y coordinate when the x coordinate is 2? 3. Yep, so you find the x coordinate of 2, you go up to the graph, read the y coordinate is 3. What are the x coordinates when the y coordinate is 4? -3 and 3. So you find the y coordinate of 4, go over to the graph, and read the x coordinates, 3 and -3. And then if we want to describe the x coordinates of all points on the graph, are there any x coordinates that get left out? No. This graph lives on every single possible x coordinate. So if I was going to describe all the x coordinates of all the points, I would just say it's everything, like it covers everything. So it was -infinity to infinity, open brackets because you always put open parentheses on infinities. That just means, we talked about last class, all the x values, right? From -infinity up to infinity, every value in between is the x coordinate of some point on that graph. All right, what if I wanted to describe the y coordinates of all points on that graph? 1 is the smallest y coordinate. This graph only lives right here and up, right? Yes, you could say y is greater than or equal to 1. The set of all y such that y is greater than or equal to 1, right? That would be set builder notation. Or you could say 1 to infinity and a square bracket on the 1 because we include the 1 parenthesis on the infinity. Should have been here last class. No. All right. Okay, so relations is going to be the topic for today. Graphing, interpreting, and modeling relationships between two variables or two sets of data is an important goal in the course. In our earlier work with graphing, we've learned that two sets of data can be represented as an ordered pair, x comma y. So for example, let's say we select Jeff Green, Avery Bradley, Keith Bogans, and Gerald Wallace from the 2013 Celtics team roster, and we list their heights, 6'9", 6'2", 6'5", and 6'9". Okay. So we could write this correspondence between the name and the height as an ordered pair, right? So we could have Jeff Green, comma, 6 feet 9 inches. Avery Bradley, comma, 6 feet 2 inches, etc. Okay. So the set of ordered pairs is called a relation in mathematics. A relation is just any set of ordered pairs. It could be finite like this, or it could be infinite like all of the ordered pairs on this graph, right? There is an infinite number of ordered pairs on there. Or it could be just a short list of ordered pairs like in this Celtics example. Okay, so the set of names, Jeff Green, Avery Bradley, etc. Okay, so the set of names, the first thing in the ordered pairs, that's called the domain of the relation. Okay? Or the inputs, the set of all first components of the ordered pairs, it's called the domain. The set of heights, the set of all second components of the relation, is called the range. Notice that I only wrote down 6 feet 9 inches once in the list. You don't have to put it twice, even though it is the height of two different players. Okay, so I could draw this sort of pictorially instead of listing ordered pairs. I could have a picture where I list all the elements from the domain, which is the 4 players' names. And then I have another picture, another set where I list all the different heights. And then I can put an arrow from the correct name to the correct height. Okay. So in the ordered pairs, we list the Celtic player first and the height second. But we could easily reverse it, right? There's nothing to say which has to go first, right? So I could write the heights first and then the names. So 6 feet 9 inches, comma, Jeff Green, 6 feet 2 inches, comma, Avery Bradley. So let's fill in the domain of this new relation. Now that I've switched the coordinates, what is the domain? The height. So I've got 6 feet 9 inches, 6 feet 2 inches, and 6 feet 5 inches. And I don't have to repeat the height that shows up twice. And then what is my range? Names. So my names are Jeff, Avery, Keith, and Gerald. Okay. And then I would just draw arrows, right? From the height to the appropriate name. So 6 feet 9 inches, I would have to draw an arrow from that to Jeff and Gerald. And then 6 feet 2 inches, that's Avery. And 6 feet 5 inches, that's Keith. All right, now suppose that the MVP award is going to go to the player that's listed at 6 feet 9 inches. Who gets the award? Yeah, either Jeff or Gerald. There are 2 players who are listed at 6 feet 9 inches. There's no way to tell who's supposed to get the MVP by that description, right? So this is an example of a relation that is not well defined, right? You can't just pick an item from the domain and it be paired with exactly one item from the range. We say that that's not well defined. So most of our work in this course is going to be focused on well-defined relations, and a well-defined relation is called a function. It has exactly one output value for any input value. Or for each element in the domain, there is exactly one corresponding element in the range, right? So if you go back over here, the fact that the 6'9" had 2 elements that it was paired with in the range, that makes that not a function. Okay. However, in the first example, there's just a single arrow from every element of the domain. So that is well defined. Every input, every element of the domain is paired with one element from the range. All right, so one more time. Which set of ordered pairs, P or H, represents a function and which represents a relation? P is a function, yes. H is a relation. So is P, right? A function is just a special kind of relation. So H and P are both relations. So somebody tell me in your own words, what is it that makes P a function? Why is P special in that it's a function? Yeah, there are no repeats in the domain. Yeah, that's a good way to check. Each person has exactly one height, right? There's no way that a person could be 2 different heights, right? So that's what makes it a relation, a function, because every person has exactly one height. But every height doesn't go with exactly one person, right? So that means that was what makes H not well defined. So when I think about functions, I always think about like my TV as a function, where I input numbers in my remote control and the output is some channel on my TV. So like if I had a TV where I type in I don't know, 807, and I got more than one channel, like sometimes I got NBC and sometimes I got Lifetime, that would not be a well-defined machine, right? That would be a bad function machine. So my TV is a function machine because for every number you type in, there is exactly one station that goes with that number. All right, so function notation. So here is a table that lists the height of a baseball Y in feet at various times X in seconds. So we throw this baseball up in the air and we're tracking its height over time. Okay. They do represent a function. Okay. Y is a function of X because for any given time, the baseball can't be in 2 different places, right? So for any given time, the baseball has one height. So it is a function. And we say Y is a function of X. Okay, so we're going to have height is Y, time is X. Instead of using the variable Y to represent a function, letters such as F, G, and H are commonly used to represent functions. And we pick F because function starts with F, and then we go with G and H because we are very creative. We go with the next 2 letters in the alphabet. Okay, so we represent the function above using function notation, and we write Y equals F of X. So that F parentheses X. You read that as F of X, like that, and it does not mean F times X. Okay, so this is just a brand new notation. In the previous math world that you've seen, writing 2 things next to each other like that with parentheses might have meant multiplication. And you will be able to tell from the context when it means multiplication and when it means function notation. So you would read that as F of X, and the input is X, the output is now F of X. Instead of Y, we use F of X. Yep, sure. So for this particular function, the input is in seconds and the output is in feet, height of the baseball. So let's look at how we evaluate and interpret function notation. So what would F of 2 equal? So 2 is an input, which means it's a time, right? So this is asking us to find the output, which is the height of the baseball, when the time is 2 seconds. Say it again. 99 feet. So f of 2 is 99. And to interpret this mathematical sentence that says f of 2 equals 99, an English sentence that would mean what that interprets what that means would be at 2 seconds, the baseball is at 99 feet. Right. And Jesse, how did you know that? Just looked at the table, found 2 seconds, look up at 99. Very good. All right, what's f of 0 equal? 3. Yep, we just go to the table, we find 0 for the time, for the input, and it's 3 feet. So this says that at time 0, which is probably the moment we let go of the baseball, right? At time 0, the baseball was 3 feet off the ground. Right. So it's probably like a child throwing the baseball up, released it at 3 feet high. Okay, one more. Now I have a sentence that says f of x equals 103. So that thing in parentheses is always representing an input, in this case time, that the output is 103 feet. So can you find a time when the height is, yeah, 2.5 seconds. Yep. So this is like an equation to be solved, and we would write x equals 2.5. Or you could rewrite the sentence putting in the 2.5. You could rewrite f of 2.5 equals 103. Whichever way you do that is fine. And this was asking us to find the time that the height of the baseball was 103 feet. So you would say the baseball was at 103 feet at time 2.5 seconds. All right, so that's enough for you to get started on your activities.